Alrighty then. Let's go ahead. I'm going to write this up. There's still more definitions. Okay. So one thing I wanted to sort of look back on. I'm going to go back here, sort of make a little bit of a change in that this statement here that we had was only half of the fundamental theorem for line integrals. We're actually now going to prove the other half. Okay. So we're going to start first by saying just what's a conservative field. That's nothing crazy here, but a vector field F with an arrow on it, which I'm going to put on, is conservative. Not if it voted for Donald Trump, but if it is the gradient of a scalar function. Okay, so that means that I do not want that. That means, let me put an arrow on my F first. Okay. F equals the gradient of some F. Okay. Okay, so now, what we're going to take as our theorem. This is the second half. You know what, I can type it out. Sure you guys are loving that. At least you would if we were in class. Not. But we're not in class, so it's a little bit different. Suppose F, and I'll put an arrow on it, is a vector field that is continuous in an open, connected region D of the plane. Okay. Suppose, I'll leave a space for the path integral. Suppose, I can draw. I have to amuse myself somehow, guys. All right, you guys aren't here for me to joke around with, so now I have my only bad jokes with myself. So suppose the integral over the curve of f dotted with dr is path independent in D. So that means, again, this integral doesn't really depend on the c, it only depends on the endpoints. Okay? Then F is a conservative field. Okay, so all right, let's go ahead and prove this. All right, so let's draw a couple pictures, or actually just one picture, but we're going to do a couple things with it. Suppose this is our region. Oh, I don't like that region. Let me erase it and try again. There, that's a good region. So now let's put a point over here. Let's make that a little darker. A comma B, and a point here, let's call it C comma D. Actually, no, we're not going to call it C comma D. We're going to call it X comma Y. Okay, now we're going to come at this thing two different ways. We're going to come here. This point here is, I'm going to call it x prime y. And this point here is x y prime. So there's going to be two different paths here. Okay? I could go this path, and then I'm going to come in horizontally. I could also go this path and come in vertically. Okay, now there's lots of other paths here. These are just two possible paths. Okay, these are just two possible paths I'm picking, but I'm picking them for a reason. All right, let's take and define, let's let f of xy equal the integral from AB to xy of f dotted with dr. Okay, so now remember, we assumed in our theorem, we assume that this integral is path independent. So it doesn't matter which way I go. These should give me the same value. Okay, so let's go ahead and take the derivative of this. Let's take it with respect to x. Okay, let's take the derivative of this with respect to x. Okay, so that's going to equal, we're going to do it along this path. Okay, now I'm going to give f a name. So I'm going to say f has a name, but I'm going to give it a name or I'm going to give it components. So I'm going to say f of xy is itself p of xy, q of xy. All right. So this integral is going to equal, this derivative is going to equal the derivative with respect to x. Now, it's going to be from a comma b to x prime comma y f dotted with dr plus, move this down a little bit, plus the partial with respect to x, the integral from x prime y to xy of f dotted with dr. Now, this first integral does not at all depend on x, does it? I should say this part of the integral. Not at all depend on this value of x. Okay? So when I take this derivative of this, that's going to give me, of course, 0. 0. Okay, so I'm going to write this as the integral with respect to x, x prime y, xy. Let me write this as, let me write this out in components. So this thing's going to be p of xy dotted with q of xy. Now, what is it dotted with? Well, x prime to x, here I have just x prime to x, so I can just say, you know what, this is just like some other thing. Let's call it, let's call it alpha or gamma, t, let's call it t. 0, but I should take the derivative of that, prime. And then we're going to do dt. Okay. What's going on here? Because x, just the x coordinate goes from x prime to x. I know it's a little confusing, but the first coordinate goes from x prime to x. So and the y coordinate doesn't change at all, does it? Okay. Actually, I should make that maybe y. But when I take the derivative of y with respect to t, it's still going to be 0. Okay, so that's going to be partial with respect to x, the integral of x prime y to xy, p of xy. Now it's going to be, I'm going to call that, let's say, dt. And that's all I'm going to get. Okay. All right, but remember, derivative in x undoes the integral in that coordinate. Ooh, that should have been t. That should have been t, damn it. Now, this video is never going up on YouTube. Okay? Don't take that as a challenge. I know who you are. All right? So, that equals just p of xy. Okay? If we do the same thing, if we go along the other path, then we would find that the derivative with respect to y of from ab to xy of f dotted with dr, that's just going to end up being q of xy. Okay, but what does that tell us? We've actually built we've built a scalar function. Okay, this is just a real number valued function whose derivative, whose gradient, is equal to the vector field. So in conclusion, the gradient of f equals our vector field. All right, that's it for this note or this video. We'll be back with another one for some problems.